All right, guys, so we're back. I'm going to put a screen up here so that you just copy this down. So the thing you need to know is that, acids react with metals to produce hydrogen gas. So what I have here is a penny. It's a 2016 penny, and so we just discussed how pennies are made of copper on the outside, but they have something on the inside. So I'm going to use my shears here and cut this penny in half. Can you guys see that there's silver in the side of the penny? You see the zinc there? So there's zinc. I'm going to just expose it. I'm going to notch it around the side with these shears. So what I'm doing here is exposing the zinc to the outside so I can react both zinc and copper at the same time to acid, and we can compare them. So you'll see here that when I notched into my penny, I cut into it and I exposed that zinc. So I'm going to go ahead and add that into my beaker here. All right. Hi, Olivia. All right, so I'm going to add acid into my beaker, and then I will show you guys what happens. So it's not going to be instantaneous, but we should be able to see bubbles forming. Do you guys see those bubbles? Yeah. Now, I'm going to just turn this beaker so that on the camera you can see how those bubbles are forming. All right, so while I let this sit here, I just let that like that, and then I'm going to reorient that like that. Okay, so I'm going to leave that picture in picture, and so that everybody can see what's happening in my beaker there. So I'm going to pull the screen down so you guys can write this down. So the zinc on the inside of the penny is reacting with the acid to form H2 gas, and that's the bubbles that are coming off. And you should be able to see that the bubbles are coming out of where those notches are instead of all over. They're all over right now, but you should be able to see that the bubbles that are coming up are coming out of the notches that I made, and that's because the inside of the penny is made of zinc. So let's predict the products of the following reactions, which are all single replacement reactions involving a metal and an acid. So the first example here is nitric acid reacting with lithium. So go ahead and do that single replacement reaction. All right, so in a single replacement reaction, the lithium, which is a metal, is going to replace the positive part of the other compound. So lithium, when it forms an ion, forms a +1 ion. I'm going to put my work above here. So lithium is going to form a +1 ion. Lithium is going to react with the nitrate from the nitric acid, and nitrate is NO3-. All right, so no need to crisscross. We're going to end up with lithium nitrate. As a result, you're also going to end up with hydrogen. But hydrogen is diatomic. So you can't end up with just one atom of hydrogen. Instead, you're always going to make two, so it's going to be H2. And that is the bubbles that you see. So that's what you're seeing happening here, and those are the bubbles that are coming out of the penny right now. Is this balanced? No, so how are we going to balance it? What do I need here for my HNO3? A 2. Where else do I need a 2 now? Yes?
Lithium nitrate.
Yeah, the lithium nitrate needs a 2, and that means that the lithium also needs a 2. All right? So, let's do another example. Our next example is going to be calcium reacting with sulfuric acid. So go ahead and predict the products of that reaction. Remember that H2 will always be one of the products. All right, and we're back. And so you know that we're going to form H plus and SO4 2 minus. You also know that when calcium forms an ion, it has a charge of 2 plus. So we're going to end up with Ca, 2 plus, and SO4, 2 minus. So no need to crisscross. That's calcium sulfate, CaSO4. And we also know that the hydrogen ions are going to find each other and form H2 gas. All right. Balanced? Yep, all balanced. Nice with those diprotic acids reacting there. So what is happening in the beaker then? What is reacting and what isn't reacting? So take out your reference tables and turn to table J. Table J is the activity series. Table J is the activity series. Activity and reactivity are the same thing in chemistry. There's no difference. I wish they just called it the reactivity series. And so what it tells us is which metals are the biggest losers. Which ones are most likely going to lose their electrons in order to bond. So lithium was our example up here. Lithium is the biggest loser. Lithium became a lithium plus 1 ion by losing its valence electron. So lithium is the most reactive. It's also the biggest loser. So this list of metals tells us which metals will react the most and which ones will not react. You'll notice that on the bottom of your table J, there's an asterisk. And that asterisk says activity series are based on hydrogen standard. No, H2 is not a metal. For some unknown reason to me, the asterisk is gone on yours, but you'll notice that on the old reference tables, there is an asterisk here to show you where H2 is. Sorry, I'll just move that. Where H2 is. H2 is not a metal, but it's on this chart to show you how metals will react with an acid. If the metal is above that H2, it will have a reaction with acid. If the metal is below H2, it will not have a reaction with that acid because it's less reactive, so it will stay in its elemental state and not do the single replacement reaction. So, there were 2 metals in the beaker. There are 2 metals here. What metals do we have here? What is on the outside of the penny? Copper. And what's on the inside of the penny? Zinc. So, see where zinc is here on the table? And where copper is here. So, according to table J, we'll see that zinc will react with an acid, but copper will not. The last 3 acids on the bottom are copper, silver, and gold. Copper, silver, and gold are in the same group on the periodic table, and they have unique properties where they don't react with things. And that's what makes them so valuable. The reason that gold is the most valuable element that exists, and we live on the gold standard in this country, the reason that exists is because of gold's very special chemical properties, being the least reactive metal that exists. Silver is the next, and copper is also in the same group there. And those are actually called noble metals, because just like noble gases, they don't react. And that's why we make things out of gold, and that's why jewelry, so a lot of people are allergic to jewelry that's not made out of those because their body reacts with it. These ones don't react, and you can, make earrings out of gold, and it won't react with your skin. If you buy cheap jewelry at like Claire's or Icing or whatever those stores are, they're usually made out of either zinc or aluminum, and that's why they sometimes turn your skin green. That's just them doing a single replacement reaction with the acids in your skin. So that's why those are the most expensive metals. So let's pull out the penny and see what it looks like now that it has reacted. All right, so time to check our penny and see how it did. I put gloves on so that I can stick my hand in here. So I'm just going to go ahead and retrieve my penny from inside here. And it's not too exciting, actually. I'm going to have to leave it overnight, I think, in this beaker. You can start to see that it has lost mass coming out of these notches here, but you'll notice that the copper is intact. The copper has not reacted at all, and instead, I'm trying to focus that, Instead, where I've notched it open is where all of those bubbles are coming out of. So I'm going to leave this overnight, and we're going to check it tomorrow. And the hope is that it's hollow, that all of the zinc on the inside reacts, and none of the copper is going to react. So we're going to hollow out this penny using this acid. So I'll just put that guy back in there. And we can see that it's going to start reacting again as soon as I put it back in there. I'll put the camera this way. And you should see that bubbles are starting to form right away coming out of those notches.